this is probably the most radical thing ever that I've made on my channel so far. And get it? Because it's a radical video about radicals, square roots. Yeah, because the square root symbol is also called the radical symbol. The reason why it's radical is because I'm here to show you what crazy appearances occur in irrational numbers, such as square roots. The first one is going to be about a square root number, which is the square root of 308,642. And you might expect it to be a totally random number, as would I, before I figured this out, which, normal numbers like, 2 or something. The square root of 2 gives you about 1.41 something, and it immediately descends into irrational patterns. But this one, however, gives you something rather remarkable and radical, too. It gives you 555,557,777,3333335111111102222222222719999970133333541111111100008, and so on. These are the first 100 digits, not including the 555 right here, because that, of course, is a whole number. I'm telling you guys the decimal digits. Look at how weird this is. You get this crazy looking repetitive pattern right here, and then eventually when you get to about here, you can already see it's starting to descend into random patterns. Well, some repeating digits are still left behind, like you see 3 zeros lined up in a row right here, and it basically just fades away. That's just weird. I had with the first 100 because it just looks like it's rational at first, but then you go here and then you start having a hard time calling it rational because it just fades away. And then the next one I'll tell you guys about is another irrational pattern. Even though it's not a square root number, I'm about to say. Still quite radical, and that is pi. Now, what is going on in pi right now? Here's what pi can tell us. So, this is the first 25 digits of pi. They look pretty random, right? Well, go to the 762nd digit of pi, and that digit is 9, and then it just goes in this weird pattern for 6 digits, and starting at the 768th digit, it goes back to being irrational. It's so close to being a terminating decimal, but it's just a few decimal places off. That's pretty cool. And this is called the Feynman point, and it's a pretty weird coincidence. And just so you don't think this is normal, the sequence 111111 happens for the first time at the 255,945th digit. And the sequence 888888 happens at the 222,299th digit of pi. Those are pretty big numbers, and that makes a lot of sense for these. But this one only occurs at the 762nd digit. Sorry, they sound a little bit similar. It does, however, end at the 767th digit right here. Yep. That's pretty weird. And then this next one is kind of weird, and it's just insane, and I want to talk about it now. This is why the number E, or Euler's number is kind of easy to remember because there's a pretty weird pattern occurring in the first couple of digits of pi. I mean, E, sorry. Got it mixed up again. So, the first few digits of E are 2.7, and then it goes 1828. And then after that, there's another 1828. And then after that, there's 45, and then 90, and then 45 again. Those are pretty weird sequences because you have 2.7 right here, that's pretty normal, but then at the second digit of E, you have 1828, and then another 1828 here. Like, this is weird. Like, why does it repeat so early in E? Like, this is literally very early in E, and you get to see this weird repeating pattern. But then we have 45, and then you just double it, and then go back to 45. And by the way, these numbers, 45, 90, and 45, can actually form a right triangle. Because we have 90 degrees here, 45 here, and 45 here. And as you learn in school, the angles of a triangle, they all add up to 180 degrees. So that does form a triangle, but there's a common mnemonic to learning the digits of E, and that is 2.7, and Andrew Jackson was elected in 1828, twice, and then right triangle side lengths 45, 90, 45. That's pretty strange. And that's about it that I can say for these weird patterns occurring in irrational numbers. If you find any more of these weird patterns, let me know and I'll try to explain them in a future episode. We'll make a part 2 to this.